We are actively trying to deploy millions of autonomous agents into the real world. From automated supply chains to unmanned aerial swarms, this push for embodied AI means moving models out of the lab and into chaotic environments. But achieving Level 5 autonomy, where systems operate without human intervention, requires a two-part computational feat. First, they need billions of hours of simulated training environments. Second, they require precise coordination once deployed in the physical world. This is where modern robotics hits a wall. Traditional continuous space simulators buckle under the data load. They render environments on continuous grids, wasting power on empty space. Consequently, supercomputing costs for reinforcement learning are climbing unsustainably. The math doesn't improve once the robots are actually deployed. Millions of agents actively navigating the real world generate a volume of telemetry that easily overwhelms classical networking controllers. Because edge devices cannot process everything locally, they offload heavy AI inference to centralized cloud clusters. That back-and-forth transit introduces latency. In a digital network, a dropped packet just means a buffered video. But in a cyber-physical system, a single millisecond of network tail latency can result in a catastrophic physical collision. Classical computing architectures simply cannot process the complexity of the physical world fast enough. To achieve reliable autonomy, the industry has to discard scalar routing and adopt a tensor-native mathematical foundation. A recent postdoctoral analysis by Julia Ochoa outlines the required architectural leap, centered on two frameworks: the Predictive Tensor Control Plane, or PTCP, and Tensor-Network Quantum Gravity, known as TNQG. This robotics integration matrix maps tensor-native algorithms directly to the industry's four operational bottlenecks: simulation, latency, telemetry, and security. The common thread is mathematical compression. Replacing continuous rendering and reactive networks with predictive routing eliminates network tail latency and reduces hardware burn rates. This is not an incremental software update, but a total replacement of the underlying physics and networking infrastructure that manages robotic fleets today. The primary bottleneck in embodied AI is the training phase. Robots cannot be trained efficiently in the real world. They require massive amounts of synthetic data generated inside simulated physics engines. But as we saw, traditional engines model continuous spatial grids, wasting vast amounts of compute processing empty space or inactive objects. TNQG functions as an operational reconstruction program. It allows developers to discard rigid, continuous space engines by calculating physical geometry dynamically. Under this framework, macroscopic geometry emerges from microscopic tensor network entanglement. Spatial distance and physical geometry are calculated as an inverse function of the robot's interaction capacity. If an autonomous agent is not interacting with a specific sector of the simulation, the environment is mathematically coarse-grained. The rendering and physics compute for that empty space drops to near zero. High-fidelity physics only materializes when the robot touches, manipulates, or observes an object. When that interaction happens, an entanglement spike occurs, triggering the probabilistic rendering of high-fidelity physical geometry right at the point of contact. By rendering physics only where necessary, this tensor-driven approach reduces the server-side footprint of physical simulations exponentially. This allows autonomy companies to train highly complex humanoid and vehicle models in infinite-scale environments at a fraction of the traditional supercomputing cost. Once those models are trained and deployed, a massive data bottleneck emerges. A global fleet of autonomous vehicles or factory robots generates petabytes of multimodal sensor data every single day. This includes LiDAR point clouds, thermal imaging, proprioception, and network health logs. Transmitting and storing this raw data centrally causes critical telemetry overload. Fleet command centers simply cannot scale storage hardware fast enough to keep up with the bloat. To manage this, PTCP introduces the Pattern of Life Tensor Train, or POL-TT, compression algorithm. POL-TT mathematically compresses chaotic, hyperdimensional fleet data into a single probability tensor. Because it is structured as a tensor, this algorithm maintains a bounded memory estimation of the entire global fleet. No matter how much data streams in, the memory footprint remains locked. This bounded footprint ensures that fleet command centers do not crash under the weight of exascale IoT data lakes. POL-TT mathematically solves the edge telemetry bottleneck, enabling real-time global observability without continuous hardware scaling. Data storage is only part of the operational challenge. We also have to orchestrate synchronized multi-agent swarms via edge-to-cloud networks. Standard networks react to packet drops after they happen. This creates network stragglers and tail latency as the system tries to resend lost data. In cooperative robotics, these reactive delays cause physical desynchronization, which can lead directly to kinetic failure and collisions. PTCP utilizes conditional value at risk, or CVAR, routing as a proactive solution. CVAR does not wait for a packet to drop. Instead, it predicts network congestion horizons before packet loss actually occurs. By calculating geodesic paths, PTCP seamlessly diverts critical inference and control data around the impending congestion. This enables remote AI inference and multi-agent coordination to occur with the near zero latency required for safe physical operation. CVAR predictive routing eliminates the reactive network delays that make Level 5 fleet coordination unsafe. As robotics and autonomous fleets become ubiquitous, they introduce severe physical security risks. A compromised autonomous vehicle or a hijacked drone swarm poses an immediate kinetic threat to public safety. Traditional cybersecurity, reliant on deep packet inspection and semantic firewalls, struggles to detect zero-day lateral movements across decentralized Internet of Things devices. PTCP introduces the D-Topo defect score, a topology-native security mechanism that ignores malware signatures entirely. Instead of reading the code inside the packets, PTCP models the communication patterns of the robotic fleet as a geometric topology, continuously calculating discrete graph curvature estimators. When a malicious actor attempts a takeover or injects an exploit to alter vehicle routing, they inherently deform the mathematical curvature of the fleet's communication network. The D-Topo score instantly flags this anomaly, triggering an automated payload-blind quarantine. The compromised robot is topologically isolated at wire speed, neutralizing the physical threat long before semantic firewalls would even recognize the malware. T-Topo provides a zero-latency kill switch, preventing cyber attacks from translating into physical harm. Realizing Level 5 autonomy requires transcending the physical limits of classical simulation and scalar data routing. This integration matrix shows how the core bottlenecks of embodied AI are solved mathematically. TNQG provides the discrete mathematical blueprint for computationally affordable and infinitely scalable RL simulation. PTCP provides telemetry compression and predictive routing to operate these models safely in the physical world. It also establishes the topological security perimeter necessary to protect these systems from kinetic hijackings. Brute force scaling of continuous space engines and reactive networks is a dead end for the robotics industry. By integrating the frameworks developed by Tensor-Networks Inc., engineers finally have the foundational architecture required to scale embodied AI safely and profitably.